We are about to start the next session, and we're starting with Professor Elliott Rouse from the University of Michigan. He's been working doing a lot of work with lower limb prosthesis, and we actually using his open source leg, and we're very happy for that development. I think the community is very happy for that. So we're glad that you could join us today, although not in person, but thanks for joining us, and please. Go ahead, thanks.
Thank you. I'm going to share my screen. Okay, can you just confirm you see everything okay? I'll take that as a yes. So hi, yeah, thank you very much for the invitation. It is a pleasure to be able to speak to you, even though I couldn't join you in person. I'm going to talk to you today about our variable stiffness prosthetic ankle foot and some work we've been doing about kind of translating that project and learning about the best way to translate it. Before I get started, I need to say that I'm an inventor on the pending patents that have been licensed by Willowwood. Before we get started, I'd like to tell you a little bit about what we do in my research group. So first and foremost, we study basic biomechanical science. And what I mean by that is we study how mechanical impedance, so the stiffness and damping properties of the joint, are regulated by the nervous system. We study perception and psychophysics. We'll talk a little bit about that today. But we also develop wearable robotic systems like exoskeletons and the robotic prostheses. But what is particularly, I think, helpful about our approach is that we pursue these in parallel and they feed back on each other. So the fundamental science questions that we answer inform the robots that we build, and we use these novel wearable robots to answer fundamental science questions. I think you'll get a feel for that. We'll talk a little bit about the modern kind of rationale for how assistive technologies are designed and controlled today. And there's usually two approaches. I'd say the first is kind of what I'll call expert tuned. So usually based on biomechanics, a researcher designs, tunes, adjusts the assistive technology, and the objective is to replicate the kinetics and kinematics, so the biomechanics of typically the healthy individual. A more recent approach that's been developed is human-in-the-loop optimization, where a physiological objective function is optimized kind of in real time. And the most common physiological objective is to reduce the metabolic rate of the wearer. So the person uses the assistive technology and a computer optimizes the settings or adjusts the mechanics of the system to minimize their metabolic rate. So let's take a step back and think about kind of maybe what happens in the real world. So I have some pictures here of some people using some prostheses, but in my research group, we think about this a little bit differently. So maybe the objective that needs to be optimized isn't a single objective at all. It's a multi-objective function where the objective changes depending on the task. You know, we behave differently when we exercise, for example, compared to when we kind of walk from classroom to classroom. Our approach is to use user preference as a way to holistically optimize across many objectives at once in a weighting that's governed by the individual, by the wearer. So they are the ones doing the optimizing, and they are the ones indicating kind of what properties they actually care about at any given time. So they kind of optimize balance, comfort, pain, effort, stability, and kind of they're the optimizer. What I want to do today is first introduce our variable stiffness prosthetic ankle foot. That'll kind of be the subject of this, and then highlight three kind of project vignettes. This is our variable stiffness prosthetic ankle. This system has two novelties. The first is it uses a cam-based transmission to deflect this leaf spring that's kind of shown there, and we can shape that cam profile to encode any passive torque angle curve of this prosthetic ankle. The second novelty is we can adjust its stiffness by moving the slider, kind of shown in this diagram, or the simple support underneath that leaf spring. And this lets us adjust the stiffness step to step by over an order of magnitude. Project vignettes that I'd like to describe to you are kind of a little bit of our path, understanding how to set the stiffness of this prosthesis, what's the best way to do it, and our concept of using user preference. So the first project vignette is what stiffness do people actually want in a prosthesis? And surprisingly, that's never been studied. One reason for that is people haven't had the ability to adjust stiffness in a prosthesis like this from step to step. The second question we'll look at is how does user preference, so the prosthesis user preference, vary from the preference of clinicians that might treat them? And the third vignette is what might be the underlying mechanisms or properties that are driving the individual to select their preference? Why do they prefer something? All right, project vignette 1, what ankle foot stiffness do people prefer during walking? In this project, we encoded a torsion spring, so a torsion spring stiffness, a linear torque angle curve, or a constant stiffness shown here. So we're looking at torque versus angle. What the user is able to do is select with a dial, so they tune a dial that they wear, and when they turn the dial, it adjusts the stiffness step to step. In this experiment, we had them walk on the treadmill, use the method of adjustment to find their preferred stiffness. We stop the treadmill, we randomly reseed the location of the dial, and then we restart. Have them do it 5 times. We get data that look like this. So in this plot, you're looking at preferred stiffness for individual subjects on the y-axis. The x-axis is our different subjects. And there's 2 things that I want to kind of highlight here. The first is people are really consistent when selecting their preferences. Their coefficient of variation is about 14%. So that's kind of remarkable. The second thing I'd like to highlight is each one of these subjects is about the same activity level and about the same body mass. So if they were being fit in the clinic by a prosthetist, they'd all be prescribed the same foot, but yet their preferences vary by a factor of about 3 times. So the takeaway here is people are sensitive, consistent, and diverse in the selection of their preferred stiffnesses. Okay, our next project vignette is how does user preference vary from clinician preference? So this is a little bit of a challenging experiment to describe, so just bear with me. But we had 7 prosthetists observe 7 people with amputations during walking. So they're observing them as they walk, just like they would in the clinic. They observed 39 trials across 13 different ankle stiffness values. And as the prosthetists watched, after each trial, they would mark on a form whether they would recommend the stiffness be increased or decreased. And the subject would also mark to themselves or to the experimenter what they thought. So everyone's trying a stiffness, or the subject is trying a stiffness, the prosthetists are observing and marking. We use these data to create psychometric functions that describe preference and consistency, and I'd like to talk about those for kind of just a minute. Before that, this is a picture of the experiment. So here you see 4 prosthetists observing the individual with amputation wearing our custom variable stiffness prosthesis. And if you look kind of in the upper left-hand corner, you can see my former student, Max Shepard, working hard at his desk running the experiment. Okay, I want to talk about these psychometric curves. So what we're looking at is psychometric functions which describe kind of preference and reliability. A steeper curve is more consistent. So here we're looking at the psychometric curve on the left-hand side for the amputee subjects. What this curve is describing is the probability that the user, when experiencing a stiffness, would select that they prefer it to be less stiff. So, and then the x-axis is the stiffness normalized to preference. So on the left-hand side of this graph, what's the probability that they want a less stiff ankle prosthesis when the prosthesis is already very soft? 0%. Conversely, on high stiffnesses, they always want the stiffness of the prosthesis to be less. So if they were a perfect sensor, this would be their answer would be a step function, where the curve describing them would be a step function. What we're looking at now is the psychometric curves for the different prosthetists. And there's kind of 2 things that I want to highlight. The first is the subject is much deeper. The subjects that are collectively shown in that are much more reliable than clinicians. So they're able to sense their preferences or what they want out of their prosthesis much better than clinicians can observe it. And then there's a potential here that I think is kind of neat to use this type of information to train or quantify performance of clinicians. So imagine like this attribute, their consistency of understanding what they want was used to guide them in training. I think that could be kind of neat. But we're looking at similar or data from the same experiment. We're looking at the difference in the stiffness of each prosthetist. So the difference in their preferred stiffness of each prosthetist. As on the x-axis, we're looking at each of the different subjects. And the colors here denote different prosthetists. So not all prosthetists observe every subject. And what we notice here, if you look at this, is prosthetists prefer about 26% greater stiffness than what their subjects prefer. So not only are they sort of less reliable, they also have a higher preferred stiffness. Okay, I want to switch gears one more time and talk about what may be driving user preference. And in this experiment, 7 people with amputation walked at fractions of their preferred stiffness at different speeds. So in this experiment, subject walked at 0% and plus or minus 30% deviation from their self-selected speed. So basically a slower pace, self-selected at a faster pace. And at these different paces, they walked at different stiffness settings, all normalized to their preferred stiffness. So they walked at 0%, plus or minus 15%, plus or minus 30%. We looked at metabolic rate, full biomechanics. We just instrumented treadmill and motion capture. And we wanted to understand what are the factors that might be driving someone's preference. And we looked at how these different factors varied as the stiffness was varied for different speeds. This is kind of neat. This is really new data. Okay, so this is for 7 subjects. What we're looking at here is on the left-hand side is the metabolic rate. On the y-axis, on the x-axis is deviation, so stiffness, deviation from their preferred. And the 3 different colors are 3 different walking speeds. So the faster, self-selected, and slower. And something we notice is people aren't metabolic rate to find their or to optimize their preferences. In fact, we see almost no measurable change in metabolic rate across the entire 60% change in stiffness here. We saw many variables that showed sort of a linear trend. What we're looking at here is peak power kind of on the prosthetic side, also as a function of deviation and stiffness. And if someone was optimizing for maximizing peak power or maybe maximizing energy return, they would make the foot be softer and softer and softer. So their preference would be skewed to the left-hand side of this curve. We found one relationship that had a optimum at the preferred stiffness. And this was a surprisingly commonsensical metric. And it was the kinematic symmetry between their sound side and their prosthetic side. And their preferences maximized their kinematic symmetry when almost nothing else was optimized. Okay, the takeaways for this talk. Prosthesis users prefer a much less stiff foot than what is available today. So prosthetic feet today are very stiff. Prosthesis users actually don't want it that stiff. They end up being that stiff because they have to help someone stand and walk, and it's foot shape. They request ESR feet or prosthetic feet today are foot shape. Prosthesis users have diverse, consistent preferences. So this, I think, means we can trust users to be the one optimizing, to be the ones identifying their preferences. Prosthetists prefer a stiffer foot. So we showed that prosthetists want a 26% stiffer foot, and that's more in line with the prostheses that exist today. Users are more consistent than clinicians, at least for now. And people may prefer stiffness values that optimizes the kinematic symmetry at their ankle. Hopefully, I kind of began this talk showing you this diagram. Hopefully you got a feel for how we use kind of fundamental science and robotics together to kind of answer some interesting questions, hopefully get technology to people who need it. This is the work of Dr. Tyler Kleitz and Dr. Max Shepard, who did a great job with these projects. And this is our new robotics building at the University of Michigan. Please come visit. And I'd like to thank my sponsor. This is supported by the Department of Defense CDMRP program. Thank you.
There, hello. There was some clapping here, but I'm not sure you heard that.
That's okay.
Do we have any
Thank you.
questions? Okay. Okay, so Levi is typing a question.
Levi's typing in a question?
Right.
Oh, no.
Did you get that, Elliot?
I think he asked, did he ask, have we run this experiment with transfemoral amputees?
Right.
That was what he asked. We are actually gearing up to run that study now. So we haven't run it yet, but I'm very interested to see how does the use of a variable stiffness prosthesis impact people who have transfemoral amputation. So that's kind of on our radar. We haven't investigated that yet. We're just now starting kind of post-COVID to ramp up for that experiment. Great question, though.
Right. Thanks. Well, thanks a lot, Elliot.
Yeah, no problem.
Yeah.